Outline. Introduction to KMap. Minterm and max term. KMap Procedure. Standard equation. Truth table. KMap mapping. KMap grouping. Final minimal equation. Example. Min equals term, 3 variable and 4 variable. Max term, 3 variable. KMap Introduction.
Maurice Carnot, a telecommunications engineer, developed the Carnot map at Bell Labs in 1953. Carnot is a pictorial method of grouping together expressions with common factors and therefore eliminating unwanted variables.
It consists of 2 n cells for n variables. The adjacent cells are differed only in single bit position. The Carnot map reduces the need for extensive calculations by taking advantage of humans' pattern recognition capability. The required Boolean results are transferred from a truth table onto a 2-dimensional grid where, in Carnot maps, the cells are ordered in gray code. In Boolean algebra, an equation can be represented in 2 forms, namely SOP and POS. Where the SOP consists of min terms and POS consist of max terms. In SOP form, the Boolean equations to be minimized are represented by sigma m. The sigma indicates sum and lowercase m indicates min terms. In SOP, the variables have value 1 for uncomplemented form, and 0 for complemented form. That is, a equals 1, and a bar equals 0. In POS form, the Boolean equations to be minimized are represented by pi_m. The pi indicates product, and uppercase m indicates max terms. In POS, the variables have value 0 for uncomplemented form, and 1 for complemented form. That is a equals 0 and a bar equals 1. KMap Procedure. Step number 1, check whether the given equation are in its standard form. Standard SOP/standard POS. Step number 2, form the truth table. Step number 3, select the KMap size according to the number of variables required and map the min terms or max terms. For SOP, put 1s in KMap cells respective to the min terms, 0s elsewhere. For POS, put 0s in KMap cells respective to the max terms, 1s elsewhere. Step number 4, make rectangular groups containing total terms in power of 2. Like 1, 2, 4, 8, etc. Step number 5, find the minimized final equation. From the groups made in step 4, find the product terms and sum them up for SOP form. From the groups made in step 4, find the sum terms and product them up for POS form. Step number 1, standard equation. Before solving a KMap, the first step is to check whether to solve for minimal SOP or minimal POS. In either case, whether the given equations are in their standard form. Example. Solve sigma m equals a bar bc plus b bar c plus abc. Here the first and third terms have 3 variables, a, b, c, either in complemented or non-complemented form, which indicated the function has 3 input variables. But second term has only 2 variables, thus we need to convert the given equation into a standard form. The procedure for the same is discussed in previous tutorial. Thus our standard equation will be like sigma m equals a bar bc plus a B bar C plus A bar B bar C plus a C bar. Now convert the given equation into equivalent binary form. Sign AM equals 1, 3, 5, 6. Step number 2. Truth table. The first step in designing a truth table is to find the number of variables required and the range. The required number of variables is decided from the standard SOP/POS equation. It's 3 variables in our case. The range of the truth table is decided as follows. Use the formula 2 power n minus 1, where n is the number of variables required to represent the biggest number from given equation in binary form. Here the biggest number is 6 and it requires 3 binary variables to represent. Therefore 2 power 3 minus 1 equals 8 minus 1 is equal to 7. Thus, our truth table range is 0 to 7. Min term, outputs are marked 1 for the inputs mentioned in question. Max term, outputs are marked 0 for the inputs mentioned in question. Step number 3, KMap size and mapping. KMap is best suited for 2 to 5 Boolean variables. Based on number of input variable we need different sized KMap. The required cells for a KMap is calculated based on the formula 2 power n, where n is number of variables. The following are some examples of KMap to find minimal SOP. The structure of the KMap remains the same except in max term the variables value are as if r equals 1 and a equals 0. Thus a small modification in KMap cell values. The following are some examples of KMap to find minimal POS. In order to make the concept clear, we like to start with a simple 2-variable KMap. A 2-variable KMap consists of 4 possible inputs as shown below. Thus requires 2 power 2 is equal to 4 cells. Let's minimize an equation using KMap. Solve y equals sigma m of 0, 3. Step number 1. Fill the truth table for the given equation. Fill output as 1 for the corresponding inputs given in question. Step number 2. Map the truth table variable into KMap. A 2-variable KMap for max term also consists of those 4 possible inputs, as shown below. Thus requires 2 power 2 equals 4 cells. But the key difference is, the max terms are represented by zeros instead of 1. Let's minimize an equation using KMap. Y equals pi of capital N, 0, 3. Step number 1. Fill the truth table for the given equation. Fill output as 0 for the inputs given in question. Step number 2. Map the truth table variable into KMap. Step number 4. Solving KMap grouping. A KMap is solved by grouping adjacent ones for minterms and zeros for max turns. Grouping is allowed only in vertical and horizontal axis. No diagonal axis grouping is allowed. Also, the group can having only even numbers of 1s or 0s. No odd number grouping is allowed. That is, we can group two power n elements only, where n equals 0, 1. The opposite corners of your KMap can be grouped, as the tables are contiguous by the extreme flanks, i.e. in a table of 4 input variables, the cells in the right column are adjacent to those in the left column, and it also happens with the boxes in the top row and those in the bottom row. Step number 5. Finding minimal term. Find the minimal Boolean equation of y equals sigma m, 1, 3, 5, 7. Step number 1. Form the truth table. Write the truth table up to the largest number. Fill the output as 1 only for the given minterms in question. Step number 3. Map the variables from truth table to KMap. Step number 4. Group them in terms as per procedure discussed. Once grouping is done, the final step is to find the minimal SOP/POS, which can be done as follows. This indicates that, whatever be the value of A, either 0 or 1, they produce output 1. So input variable A has no effect over output. Thus we can neglect A. This indicates that, whatever be the value of B, either 0 or 1, they produce output 1. So input variable B has no effect over output. Thus we can neglect B. This indicates that, output follows, input C. Thus we have to consider C. KMap. Special case 1. Minterm to max term or max term to minterm. Sometimes to make questions a little tough, the questioner may ask to find the minimal equation of a particular form, but the question given might be in other form. Obtain the minimal product of sum y equals sigma small n 0, 2, 3, 6, 7. Here, the given variables are in terms of minterm, but the question is to find the minimal POS, that is minimal max terms. In a given range of variables, the variables that are not marked as minterms are the max terms. Step number 1. Convert SOP to POS. If y equals sigma of small n 0, 2, 3, 6, 7, then the biggest number is 7, thus our range is 0 to 7. Therefore, y equals pi of m, 1, 4, 5. Remaining procedures is same as solving max term. KMap. Special case 2, don't care terms. In some logic circuits, certain input conditions never occur, therefore the corresponding output never appears. In such cases the output level is not defined, it can be either high or low. These output levels are indicated by X or D in the truth table. A circuit designer is free to make the output for any don't care condition either a 0 or a 1 in order to produce the simplest output expression.
Thank you for watching. Please leave your valuable comments and subscribe our channel for new tutorials.